Hello, this is Constant Velocity Motion Lab video that will show you some facts about second Newton's law. So, we begin with the tracker video that shows how the train moves along an horizontal track that is a desk, and we can see the train moving along it. So, from this, I obtain the real data about the motion of the train's constant velocity. So we begin with the initial position x equals 0.001 meters at the time t equals 0 seconds. So from this data we have to find the initial velocity of the trains. So we can obtain that by doing the division between the displacement of the train by the time interval that I take from 0 to 0.034 seconds. So for this, I obtain that the initial velocity is equals to 0.5588 meters per second. We have the initial position, that is the vector with coordinates x 0.001, 0 in the y coordinate, and 0 on the z coordinate. We have that the final time of our experiment, or the real experiment about the train, is 1.077 seconds at the position 0.382. So there's the data that we can get from the tracker program, and now we're gonna move on with the Python program. This Python program is made to get the ideal model from the train moving about a horizontal track. So we could see that I set the initial velocity and the ball position that simulates the ideal train that we have in this program. So this is the ball position and this is the ball initial velocity. So I'm gonna move on for the part that is the most important of this script. This part of the script is necessary to apply the second Newton's law. So I say that time that doesn't exceed what it was the last time recorded on the tracker program on the real case of the train moving along the desk. So for this, the time was 1.077 seconds. So I established for this script that the time wouldn't exceed that time. The time 1.077 seconds. So I will run. So first, I need to establish what the second law. So we have here that for this case, because we have to simulate a constant velocity motion, we have to establish the net force to be as 0 Newton about all its coordinates, like x coordinate 0, 0 coordinate y, and 0 coordinate z. So we're gonna move on to the slide to show this. So this is what I'm doing. I'm setting that net force by the vector 0, 0, 0. So this says that there's no force exerted by any surroundings. So this will be equal to the constant velocity or no motion about the train if the train will be at rest. So I run the Python model, and what I obtain is a straight line that shows the time versus position. So we can see, or we can estimate, that the position at the last time that I put in the program is about 0.6 0 meters. That is in this part of the graph, in about the time that I said, that doesn't be more than 1.077 seconds. Now I will show you the graphs about the time versus position from the ideal model, from the real model. So we can ignore there is some friction for the decks and on the wheels of the train. So that's the difference between these two graphs, the ideal model and the real model. So we have this difference about the motion of the train because there is some friction about the train. So for the real model, we have the final position of the train is in 0.382 meters. That shows that this train is not moving at constant velocity. So for the what if question, I'm gonna move to the Python model. I'm gonna change the net force vector. I'm gonna change it for the values -0.35. That means that this force is exerting from the train, the ideal train, in the negative direction for the motion. So we're gonna see what will happen. So for this, we have obtained that the position of the train is less than the other model, the ideal model. So for the same interval time, we can see that we obtain a position of the train that about 0.39 meters. That we can see it in the time versus position graph about the ideal model, the real model, and the friction model. So we can see that it fits a little well about the real model with estimation of the net force about -0.35 newtons. So we can see that if we have or we need to show a constant velocity motion, we have to in the real world to eliminate the friction model, because this is the why we can obtain for the real data that the ideal model fits with the real model. Thank you.